Good morning, folks. This is a short video to emphasize the importance of achieving optimal data acquisition. Now, these short videos are really just supposed to emphasize things that you will have in the course notes or in the reading or whatever, but the idea is to emphasize them because I think that a video is perhaps a bit more sort of emphatic than just reading through a whole slew of stuff. So this is quite an important one. It's called Achieving Optimal Data Acquisition, and basically I want to try and emphasize to you that with carbonates, unlike simple clastics, we do have to be careful that we have actually acquired all of the required data, and we must do that early on, even in the well planning stage, not just in the drilling but in the well planning stage, because of course acquiring data requires equipment and requires a budget, etc. So the key things that you must do is that you must think about whether you have the reservoir rock type identification, whether you've got the data to identify the RRT or the reservoir rock type. In other words, you may need an image log, for example, or you may need more than just your routine density, neutron, resistivity, and sonic. You will probably need that to identify the reservoir rock type, which is essential because, of course, each reservoir rock type has got its own reservoir rock type equation set. Now, what is a reservoir rock type equation set? You probably already know, but it is basically a set of equations that take the data that you've acquired. Let me just put myself in the corner there. That take the data that you've acquired, the raw data that you've acquired, into the required inputs for the geological model. So there'll be a set of equations that take the rho B, etc., and resistivity through a set of equations, and then you get your porosity, permeability, saturation, residual oil saturation, perhaps net pay, etc., and you put those in the geological model. And of course, the third thing you must do always with carbonates is, particularly if they're old, old or deep, you must have some way of identifying fractures, at least to know that if they are a significant feature of your reservoir or not, because they often will be in a carbonate reservoir. Okay, so unless the entire section is cored, petrophysical data must include all data required for clastics, plus reservoir rock type identification, routine core analysis and special core analysis pore geometry data to establish each equation set, each reservoir rock type's equation set, and something to clarify whether or not we have fractures. And then going on, of course, after we've done the kind of petrophysical bit, we need to actually test whether each reservoir rock type that we're going to be counting in our reserves has actually got the ability to flow hydrocarbons at a commercial rate. So we need to have some wireline formation tests or some conventional well tests to actually flow hydrocarbons and collect samples from each major reservoir rock type. With carbonates, you're not just thinking about a carbonate reservoir, you're thinking about the different rock types that are almost inevitably within that reservoir. So you'll probably have a dominant reservoir rock type that's got maybe 70% of the hydrocarbons, and you'll also have one or two other minor ones that have got a smaller hydrocarbon pore volume or are not going to contribute so much to the reservoir in the reservoir's life, but they are still a significant and commercial, part of the reservoir. Number 5, accessory information to clarify and support the reservoir rock type identification, the characterization of that rock type in terms of equation sets, and fracture identification. Now, a little note I've got for you here, folks, is that we tend to collect bits of information in bits and pieces, but it's much more cost effective and much more powerful petrophysically if you can have focused core tests and special logs are all acquired within the same interval of your best high hydrocarbon pore volume permeable reservoir rock type, not in different wells. Now, of course, the trouble is that you may not really realize what is your best reservoir rock type. You and the geologist, it'll always be not just you, it'll be the geologist as well, because the geologist understands the way that lump of rock is populating the whole structure, whether it's a significant volume of rock or not. If it looks very good in your well, but it's only a tiny volume of rock, then of course the geologist will say that's not really an important reservoir rock type. So we don't need to focus too much on that one. If it's a section in your well which looks good and also has a significant volume, of course we need to characterize that, because that's where our reserves are going to come from. Now do that if possible in the first well that you drill, or an early well, and say this is our reservoir rock type. We need to stop, we need to cut some core, we need to test it, we need to get some samples, we need to get some pressures, do everything in that one interval. And then why do you do that? Because when you do your cross calibrations to get to your answers from your log data only, you've got a nice tight little consolidated little packet of information that's all tightly correlated, and you haven't got to worry about the different mud system they use, the different borehole they use, whether they use a different logging tool for this well or that well. All of that stuff is common, and so the equations you get are going to be tighter than if you got them all over different wells at different intervals. Okay, right. So that's really the main thrust of what I wanted to say. Just a little reminder from Aguilera, who's of course the reservoir engineer who's done hundreds of, well, I don't know about hundreds, but lots and lots of fractured reservoirs studies. Each naturally fractured reservoir is a research project in itself. In my experience, this also applies to many tight carbonate reservoirs. Some carbonates are homogeneous, and so reservoir rock type identification is less crucial because we've basically got one rock type. But the equation sets for that reservoir rock type, of course, are important. We do still have to take the raw data, which is the logs, the cheap data, through the equations to the valid geomodel inputs. So you as a petrophysicist, when you're planning the well with your team, when you're sitting down, hopefully you do this, you sit down with the geologist, the engineer, the people who are going to drill the well, the drillers, and the mud people, and maybe the logging contractor, and you ask yourself the question, what logging tools address 1, 2, and 3? You know, these 1, 2, and 3 up here. Have they been run, or are we planning to run them? Have we got the budget to run them? And as I always say, you know, to my students, you need to take responsibility for acquiring the data and making the team or the exploration manager realize that certain types of reservoirs are more expensive to understand and to know, to build, in order to build a geological model which is fit for purpose to make valid commercial decisions. Sometimes we have to spend more money in acquiring the data to do that, and more money on the petrophysical expertise to achieve that fit for purpose geological model. And that's always my objective, to make a geological model which is able to make, you know, meaningful decisions about the future of how we're going to develop this reservoir. Okay, folks, well, that'll be all this will be, you know, hopefully you've seen it already or you're going to see it again, but this is quite an important slide because we are acquiring the data here. Okay, thank you.